Hello friends. So as before we have derived expression for heat transfer through cylinder, now it's time to derive expression for heat transfer through hollow sphere. So there is a similarity between both hollow sphere and hollow cylinder because both having the same cross section area. If you cut the cylinder into that cross section and the sphere, we will getting the same shape, that is a circular shape. So the diagram will be same in both cases. Now so for that derivation we must have to consider hollow sphere through which heat is going to transfer. So for that let us consider Q as a rate of heat transfer. It is not a quantity of heat transfer, it is a rate of heat transfer. So that joule per unit second we will convert into watt. Then area again, that cross section area of the sphere will be in the meter square. T1 and T2 are again inside and outside temperatures of that sphere surfaces. K is the thermal conductivity of metal hollow sphere. So since that sphere is also made up of some solid material, it is hollow but the material of metal is that solid. So heat going to transfer by means of conduction. So we are using again by using Fourier's law of heat conduction. So for that case dq is equal to Ka T2 minus T1 upon dr. So again here the replacement factor is area because now we are going to use the area of that section, that sphere section is 4 pi r square. As we know that the surface area we are considering for the sphere here, so 4 pi r square will be there. So replace that factor here. dq is equal to k in a bracket 4 pi r square T2 minus T1 divided by dr. So again here what is dr? Dr is the main parameter, you must have to consider that because dr is the elemental thickness. For that strip of elemental thickness we are going to integrate it to complete the entire sphere from that and to get the expression for complete sphere here. So for that strip we are considering the thickness as a radial thickness, so dr is that radial thickness here. So transfer the parameter here. First of all we convert that dq, the small heat going to convert into the large amount of heat. So integrate that dq from 0 to complete q is equal to k in a bracket 4 pi r square T2 minus T1 divided by dr. So now what is the integration of 1? As we seen earlier, the same things are here. Integration of 1 will be q is equal to k in a bracket 4 pi r square T2 minus T1 divided by dr. Again the changing variable parameters is dr. Again that dr should be transferred to that side to again integrate it. So q will be as it is. Now dr is there and the variable of that dr is r square. So that side, the RHS side of that r square is multiplied. So we have to transfer to make it divide. So dr upon r square is equal to, the rest of the parameters are 4 pi k. Then what is the rest of the parameters? You see that 4 pi k T2 minus T1. Now integrate it to make it large. So integrating this entire equation, integrating from R1 to R2. As we know that inside radius R1 and integrate it up to R2. So the boundary conditions are R1 to R2. So integrating R1 to R2, 1 upon R square dr is equal to 4 pi k T2 minus T1. As we know that integration of 1 upon x square. So if you know the derivative of 1 upon x is minus 1 upon x square. So if you are integrating 1 upon x square, you will get 1 upon x here. So integration of 1 upon x is minus 1 upon x because they are anti-related to each other. So once again, if integration of 1 upon x square is minus 1 upon x, so integration of 1 upon r square will be minus 1 upon r from limit r1 to r2. This you must have to understand here the logic of solving the integration. Once again I am telling you, in derivative of 1 upon x is minus 1 upon x square. So ultimately integration of 1 upon x square is 1 upon x. You have to transfer this minus sign to that side to make it integration of 1 upon r square minus 1 upon r from r1 to r2. So in this way we have solved the integration. Now rest of the parameters is as it is 4 pi k T2 minus T1 here. So replace that parameters, that limits, upper limit we have to first put here, then minus sign, then lower limit. So if we did like that, so we are getting the minus sign will be outside, 1 upon upper limit, that is R2, minus 1 upon lower limit, that is R1. So this R we are going to replace with upper limit R2, then minus sign, then lower limit R1. So in this way we are solving this derivation. 4 pi k T2 minus T1, this side will be as it is. Now we have to transfer this minus sign so that the plus term will get minus and minus term will get plus. So 1 upon R2 minus plus 1 upon R1 is there, is equal to 4 pi k T2 minus T1. So now cross multiplication will be there. So Q is equal to RQ into inner bracket minus R1 plus R2 divided by R1 into R2. Once again we are multiplying this, both the cross multiplication, R1 minus will be there and R2 plus will be there, whole divided by cross denominator R1 into R2 is equal to 4 pi k T2 minus T1. So you can write it, simplify. Q is equal to finally 4 pi k R1 into R2 T2 minus T1, because this is the divide term, should be come to that side, multiply, whole divided by, this will be the term R2 plus minus R1. So this is the derivation for heat transfer through hollow sphere. Thank you.